Hey, welcome back to the PCSN training material. What you just saw was me manipulating the natural laws of the universe, physics, so that I could do fancy tricks. So you're going to have this kind of background knowledge with C++ in order to be a good programmer. You're going to need to know how information ends up behaving, how the language behaves, and how the computer behaves, just so that you can manipulate those things to do whatever kinds of fancy tricks that you require. So hopefully by the end of today's video, you'll be able to fool around with some variables, fool around with a couple beginner programs, and start to manipulate things and start to get a feeling for how the language works. So without further ado, let's jump right in.
First off, this video is going to be in a little bit of a different format than the last one. So the last one we just looked at pure code. We just looked at conceptual stuff. So now we're going to see, obviously behavior and decision making. So we're going to actually do some code compiling and code running. So I'm going to be compiling over and over, so that's why I have this guy up. Alright, so this main program should right now just only output hello world. So let's look at what we're going to be working on. So we're actually working in this directory. Notice that I actually previously compiled a program. So I'm going to run this command. It's clear the screen, remove this file called program, and then use G++ to compile main.cpp, and then output another file called program. Okay. Now again, you don't really have to worry about this if you're compiling using some other kind of tool, like code blocks, for example. That might be a little bit of an easier way to compile C++ code for you. I'm just using this method because I'm working on a Linux system, and this over time has been a lot easier and less fussy for me. So we're going to run this, and then we're going to actually run the program that we just compiled, and it says hello world. It's just exactly what we expected. Okay, so note the size of the file. I have all these functions, and they're all collapsed like this. Okay, so these, and we're going to talk more about like how to actually make functions, what are the rules and everything like that. But for now, you can kind of just know that these braces make the body of the function. It's going to have some kind of return type. It's going to output some kind of type, and that's pretty much what all these do. But we're going to examine how this language does stuff. On the technical side, when you're actually doing any kind of operations inside main, whenever you're running any kind of program, you're storing any kind of variables, your program, the actual computer, the hardware, has to juggle around all that memory. Notice that when I was talking about scope before, I was basically trying to imply that anywhere within these braces, underneath where variable is declared, is within that variable scope. You can access it anywhere below that declaration within these braces, within at least its nearest encasing braces. So if I have like some kind of if statement inside here, and I declare a variable inside there, it would have to stay within that if statement. What the computer is actually doing within this, say if I had some kind of weird structure like this, and I had some kind of encasing set of braces like this, and then I said int my int, when I hit this other brace, the computer actually goes, oh, I'm no longer going to be using this because I exited its scope. So it actually gets rid of it. It just trashes that variable. It doesn't use it in memory anymore. It still exists within the program, and if you call this section of code again somehow, it will still use it again. But as soon as it hits here and exits this area, this set of braces, it destroys this information. That's not to say that if you move my int to outside of the if structure, when it hits here, it doesn't really care. It still exists because this would be the next nearest encasing set of braces. Okay. While this might seem like it's a bad idea to destroy information, it's actually a very good thing because the computer that you're programming on, no matter what, has a very limited amount of memory. Even if it is 12 gigabytes of RAM or something like that, you can absolutely run out of 12 gigabytes of RAM if you have a memory leak in your program, or if you're not managing your memory properly and doing high amounts of computation. But this is especially relevant if you're worried about operating on very low-level hardware, like something like an Arduino Uno, where you only have an 8-bit processor. Remember, again, what I said about variables having scope anywhere below their declaration, which is actually what's going on here in my global int. This is called a global variable, and because it's in global scope, it's declared before main and outside any braces, so it's accessible everywhere. Okay, but if I moved it way below here, it hasn't been declared before main, so main can't see it. So it would have to be declared up here. Globals are generally not supposed to be so great because they stay in memory all the dang time. They never go away, and you usually want to reserve that for special information, and you usually want to minimize that. But this kind of scope rule actually works the same way for functions. So like if I have this function, example of assignment, I can actually use this function inside this function if I want to call it there. But if I want to use this function, some math underscore check if even, if I want to use this function inside this function, I'm not allowed because I didn't say that one first. Okay, so it's still, you're interpreting the code top down. You know, you're reading it left to right, top down. Okay, so now let's actually test this scope stuff. So we're gonna say hello world, but then we're going to output the value of my global int, which I would expect it would just say 20. So let's get rid of the file and recompile. Okay, there we go. So there it output 20. Alright, let's do that again, but let's declare a variable after. So we're going to declare this here, but we're going to try to output its value before its declaration. Alright, let's save that, and then let's clear the screen, recompile. Alright, we got an error. So it says cout, and it's pointing right here. Alright. And I had predicted, hey, this is not going to work, and you can also see my comment there. So the error is on the my no scope int. I named it that because it's not in scope. It's trying to be used before the declaration. So it says it was not declared in this scope. That's the error. So let's correct that by moving the line up, and then let's clear the screen and recompile. And then run the program, and it outputted my global int, and then my no scope int, which is actually in scope now. So this is actually called a local variable. If it's declared within some function anywhere, it's actually going to be a local variable, and this is going to be a global variable. Global meaning that this is actually accessible everywhere. Now we're going to talk about assignment. So assignment is basically the action of storing information into a variable, and you could also think of assignment as talking about doing math at all. And now we're going to be couting. This is the output to the screen. This is what we use to say hello world. You know, this is how we output information, and this is using the IO stream, just a reminder. So we're including the IO stream so that we can get access to saying things on the screen. We're running the example of assignment function. So what this thing is actually doing in the background is this is actually adding these two and then just outputting that. So then this ends up getting replaced with that number. That's called evaluation. And then we're finishing that off with a new line character. So we're going to clear this, compile the program, run it again, and 5 plus 9 is 14. So let's actually take a look at this function. Let's open it up. We're saying that this is going to output an int, and both of the inputs are integers. And they're called some nickname A and B. So we're just going to refer to them as A and B no matter what on the inside of this function. We can declare a local variable and then store, you know, this input into that if we want to. We can store, you know, that for both of them. We can also do something crazy like this where we can, you know, add the values together and then store that into this. Or we can just add one, or we can do something special, because adding one is so common in C++ and in programming generally, that there's this increment operator where you just do the variable name and then a plus plus or a minus minus if you want to go down just one step. This is also another way that you can do up one for that variable. So if I had 5 in this to start off, then it would have 6 after this. When you do it this way, it does this operation, and then it basically says do this. So this is like shorthand for this, and this is also shorthand for this. But this would be shorthand for this if this was a 5. Okay. This is also going to be shorthand, but this is this same operation, but if this were a subtraction operation. It's the same deal with this, except this would make it multiplication. In the end, we're not really doing anything with any of this information. We're actually just creating a variable called results. It's an integer, and we're storing the sum of a and b, and storing in that, and then returning it. So now notice how we're actually calling this function. We're just calling its name and then using some parentheses and inputting some information. So this is also going to show you how, if you don't use the correct data type that the function is expecting, you're going to get mixed and unexpected results. Like if I do something like 5.5 plus 9.2, that's going to end up with a decimal, but the program isn't going to agree with you. 14. The reason why that's 14 is because when these floating point numbers end up getting input into this thing, this is going, no, that's not decimal. So then it just chops this extra information off, which is called truncation. It truncates this information, and it only keeps the 5 integer. And then after this thing is done doing all of its operations and stuff like that, all of its magic, it just replaces it with whatever value that it figures, which the truncated 5.5, which is 5, 5 plus 9 is 14, so it just replaces this with 14, spits that out on the screen, and then finishes that off with a new line, which is why this starts back off over here instead of right here. So just to show that actually happening, because I want to show how careful you have to be about your formatting. That's weird to read. That's harder to see in my eyes. There we go. Alright, so we're going to check out a little bit more arithmetic to get a little bit of a feel, more of a feel of what you can really do in C++. So we've got this other function called sumMath check if even, and we're inputting the integer 2. So let's check out what this function is doing. When you want to do math on integers in C++ or in Arduino, you're going to have these things available to you. You're going to be able to add, you're going to be able to subtract, you're going to be able to multiply, you're going to be able to do an integer division, and you'll also be able to do a modulus. Now the modulus is the same thing as division, but instead of giving you the whole number, it gives you the remainder. So 5 modulus 2 would be 1, because there's one remainder when you divide 5 by 2. So when we run sumMath underscore check if even, and then we give it some integer, we do modulus 2, and then depending on whether or not that returns a 1 or a 0, because if it's returning 0, then it's an even number, because 4 divided by 2, there's no remainder. 5 divided by 2 returns a 1. So the if statement would actually evaluate to true if the result turns out to be a 1. And if this actually evaluates to a 0, it runs the else statement. If sumint modulus 2 returns a 1, then this is going to return a false. So this function is saying check if even, false, it's not even. If this evaluates to a 0, then we know that this is even. So then we want to return a true. The key here is just remembering that this if statement is going to say run this first block if whatever is in the parentheses is 1. And if it's a 0, it's going to say run the else statement. So now let's actually test this function out. So we've commented out the other thing, replaced it, saved the file, clearing the screen, recompiling, and then rerunning the program. 2 returns a boolean true or an integer 1, so that's even. Alright. What about 5? Is 5 even? False. What about 25? False. 20? true. So it's actually detecting that this is even now. Now, if you were paying attention before, I specified integer division because there's actually multiple kinds of division. There's integer division and there's floating point division. Integer division doesn't take care of decimal places at all. So we're going to show 11 divided by 2. We would expect a decimal point to show up. 11 divided by 2 should be 5.5, but it's actually only returning a 5 because it doesn't give a crap about the 0.5 that's tacked on. Now, what about if we do a 0.0 on one of these? That changes what the compiler recognizes as the number. That then turns this entire operation into floating point division. Once one of these goes into a decimal point kind of format, then the entire thing gets turned into floating point division. Let's try again for the 11. Yep. That was the same behavior that you saw at the examples of assignment function with the 5.5 and 9.2. So now we're going to talk about arrays. I think I've said before that arrays are basically just lists of some other data type. They're just one after another. They can be whatever size that you want. Of course, it's going to be limited by how much space you have given by your hardware. But other than that, you can pretty much store any kind of data type in a list, and you can access that using an index. Here, we're going to start using this function. This is another function that I made, crazy arrays underscore get array values. So this is a function where we're going to pass in 5, an integer 5, and it's going to get us back the values stored in position 5 of the array that I declare inside this function. So we're going to go over here where this function is declared. I think I want to try to make this a little bit easier to read, so I'm going to split this down. And then I'm going to open this again over here. So this is just to show what main is doing, and then over here we can actually examine what's going on inside the function. So this is just a dual view of the same file. Here, if we edit something, it'll actually change it in both sides. Here we're declaring a C string. It's a character array. It has 15 positions available. Now, this is just saying blah space blah space blah. These space characters absolutely count as a character. If you count all of these characters, you'll actually get 14. But you do have to remember that because it's a C string, the computer's hardware needs the null flag at the end of the string of characters to tell it that it's reached the end of the string. So if we actually try to use 14 when trying to compile this, then this is actually going to error out. Let's actually recompile this and run the program. So it accesses position 5 of this array, which is declared here. So this is position 5. I just stored the integer 5 in position 5. So then it spits out 5. We'll change this around in a sec to make this a little bit more clear. But right now I just want to focus on making sure you know that if you actually try to compile this with the wrong size, it'll tell you no. Yeah. Error. Initializer string for array of chars is too long. So the initializer string, blah blah blah, for this array of characters is too long for this storage because there isn't enough space to store that extra null character at the end. So let's fix that. So again, this is just a very explicit way of defining the elements inside an array. Sometimes this is more useful. Most of the time when I'm dealing with C strings, this is not very useful. Most of the time this is more useful if I'm dealing with trying to make a map of something. Now notice when I declare the C string, I'm not actually putting any kind of numbers inside here. This makes it automatically size itself based on the data that I put in to initialize it. Here I'm declaring a character array that has 8 positions, but I'm not actually defining it. So it's just empty. And then here, I'm just creating an integer array, which I'm actually using to output for the function. This is the only one that I'm actually doing stuff with. So you can kind of think of those as by themselves. So this index actually starts from 0, and that might be a little bit uncomfortable to think about, like starting your counting from 0 kind of really often in computing, but it's kind of something that you're going to have to get used to. So if I want to reach for this value, then I would call position 0. There we go. And just to make it very clear that this is actually accessing this data and not just passing this value on through, let's actually change this to 1010. See? This is actually spitting out this information itself. The next part that we're going to cover is actually a pretty huge part of programming, and pretty much no matter what procedural language that you use, you're probably going to end up using something like an if-else kind of construct. Let's just dive right in. So this function right here is inside our main. Alright, so we do hello world. Let's just collapse this to make that a little easier. All of that's obviously commented out because it has all the slashes in front. So we're just going to hello world, and then we're going to run the if-else construct stuff. If we just look on the inside of this, we just have returns on the inside of these if-else structures. So it's not actually outputting anything. So we shouldn't actually see anything when we compile it to the screen. And yeah, so there we go. This is expected because we're not using cout to actually output anything to the screen. So what this is actually doing is it's just compiling it. We know then that all of this code is legal because it doesn't complain at us with compilation errors. So first off, we have just a simple if statement. We have an if, we have a condition, which is inside here, inside the parentheses, and I just have the Boolean literal true here. So this is just going to always evaluate true and run this. I can put whatever I want inside the if statement. If you need some more complexity, you also have the if-else statements, which basically says if this is true, then execute this first block. If this is false, though, then it just does this else. So this must be true in order to run this. Otherwise, it just, every other case, it runs else. So now we have if, and then else if. So, and then we have another else if, and then another else if, and then an else at the end. So we can actually have as many else ifs if we want. So here, with this if else, we have only one situation where we're checking the condition. Here we might want many conditions that we might want to check in order of precedence or in order of importance. So what I actually have inside all of these conditions is actually a little bit interesting, and it sheds a light on the concept of truthy and falsy. It's basically how are values seen inside the condition with respect to the binary values that everything has to evaluate to. Because everything has to evaluate to either a true statement or a false statement in these conditions, no matter what. So, what happens when you have something complicated like a C string or a null character? What happens? So really the trick here is something is falsy if the binary bits that are used to store it are just all zeros. So something like integer 0 evaluates to false, just like Boolean literal false. There's no conversion that happens here. This gets converted to a Boolean false. So if we want to test for truthy and falsiness, we can actually just make any kind of variable that we want and then just put it into a structure like this, and it'll evaluate it and actually tell you what it thinks it is. So let's start off with an empty string, and it's going to say truthy if it thinks that it's true for the empty string. If we want to check to see whether or not a empty string is a falsy kind of statement, let's compile this, and as you can see there, it actually is truthy. So that's how you can actually check that. And the reason why the empty string is truthy is because there's still the null character. There's still something being stored. Alright, so let's check a full string. That's truthy. Let's check a null character. Recompile. That's falsy. Let's check some integers. 10. Do remember to save every time you recompile. So 10 is truthy, but integer 0 is falsy. Let's actually make this into an empty character array that is 5 positions large, and let's not define it, to see if we can force it into being as falsy as possible. And it's still truthy. Still truthy. So this truthy, falsy kind of property of all values within programming that you can use within conditions is actually a really convenient way to check statuses and control program flow. Okay, so now that we've covered ifs and else statements, and we've covered a little bit about truthy and falsy, so we know how to use that condition check very well to control program flow. Let's introduce a different construct that's basically like a shorthand version of an if-else statement, which is called the ternary operator. Here we're using ternary check-if-even. It's going to be similar to the other check-if-even function that we used in the past, which was sumMath underscore check-if-even. So this is the if-else structure for the old one. Now let's look at the new one. This here is actually the ternary syntax. So you start off with a set of parentheses and a question mark. That question mark denotes, hey, this is going to be a ternary statement. The parentheses have the condition, works just the same as before, and then if this condition evaluates to true, then it runs this first block that's separated off with a colon. If this condition is false, then it runs the false block. Here we see us actually using it. So we have our ternary operation here, our output if this block is true, and our output if this block is false. So once this actually evaluates and it turns into the remainder after input even or odd is divided by 2, if that results in a 1, that's truthy, so that runs the true statement, or that runs the first block, because that's what automatically runs if it's true. Just like the if this is true, then run this first block. Same thing for this. If this is false, then run this second block. Here we're using the ternary operator to return a value and store it into some variable. If we want to use it as the output of the function, we can just use return and then the entire ternary operation. So let's actually test this out. Here we have 15. Last time I compiled, it said 15 was odd. So let's go, alright, show me 14. Recompile, rerun. Alright, 14's even. Let's look at 8. I'm expecting an even. Okay. Let's go to 9. 9 is odd. I'm expecting a 0, indicating that it's odd. Okay. So now let's also check 0, because 0 should have 0 left over.
Now we're going to talk about looping structures. A lot of power comes from the computer being able to repeat some action but slightly modifying how it does that action each time. The first loop structure that we're going to talk about is the while loop, seen here. In English, this would read, while this condition is true, do this. So this will actually repeat this body of code until this condition is no longer true. Something that you might use this loop for is for logging some kind of data set every second to an SD card, or you might want to do something like check for some special characters in some C string, like this function does. This function declares an array position integer, a space count integer, and then it has this C string, good morning starshine, the world says hello, exclamation point. While my C string at this position is not equal to null, which remember is at the end of all C strings, and then it checks to see if that character is a space character, and if it is, it counts that space. It increments up the space count variable. And after it tallies up another space, it then moves on to the next array position. It repeats this until it hits that null character at the end of the C string. After all this, it outputs the space count. So all in all, this function basically just counts the number of spaces in this string and then outputs that. Alright, so let's actually compile this. So it counts 6 spaces in good morning starshine, the world says hello. Go ahead and count it. Just to make sure we're not lying. 1, 2, 3, 4, 5. Recompile. 11. Alright, let's move on to another example. Now here I'm just running complex conditions function, and then right after that semicolon I'm outputting to the terminal another new line. Notice this kind of code is still legal as long as I still use those semicolons. So the complex conditions function is checking for whether or not we're at the null character in the C string, and then it checks for whether or not the current character is a period, a question mark, or an exclamation point. And if it is, that part is true. But notice everything is within a set of parentheses, and then outside of that set of parentheses is an exclamation point, which inverts that logic. So if any of these return true, this turns that false. So all in all, this equates to if the current character is not a period, a question mark, or an exclamation point, then output that character, and then count up the array position. So this is sort of doing something similar from last time, but instead of counting how many spaces we want, we're just outputting all of this string except for all the punctuation marks. So let's actually test it. Beware though, with great power comes great responsibility. And the danger here is that you're sending your computer off to make decisions without explicit instructions. Loops can be dangerous if you accidentally make a loop that doesn't have any way of exiting. Remember that the computer is only going to do exactly what you tell it. Nothing more, nothing less. So if you accidentally tell it to jump off a cliff, it will absolutely do that. This would be something called a logical error, in that the program still compiles, so it's not a syntax error, but it's not doing the intended job. Here's an example of an infinite loop. So let's just run this function just to see what ends up happening when you do an infinite loop. And I'm just going to repeat this one action just to give you some sort of visual indication of what it's doing. Now notice the loop says while true. This is a Boolean literal, which never changes. This will always loop forever until I kill it. So let's compile this. Yeah, that's bad. Stop. So this is a good example of how to make an infinite loop on purpose. But I really want to make sure that I show you how you can make an infinite loop on accident. So let's look back on the complex conditions function. So here we end up doing this while loop that checks for the null character. But that's the thing, is that it's checking for the null character. What if you never see that? How can you never see that? What if you never move on to the next character? Let's look at this here. I have this modified just a little bit so that it actually does come up with an infinite loop. Notice the change? This array position is outside of the while loop, so you never actually increment up the array position. And you want to have this after the if check because you don't want to miss the first character. This would result in an infinite loop and can be pretty easy to miss. And then let's try this. See how it's only printing out the first character? Stop! It never actually increments up to the next character position. So now on to the next loop structure. So we just covered while loops, and a lot of the information that we just covered with while loops are going to apply to do while loops. So do while is almost exactly the same as a while loop, except that the condition check that is normally at the top of the while loop is then at the bottom. So this in English would read, do this while this is true. So functionally, when you run this code, this while loop, if this condition is not true for the first loop, it'll just skip over this whole while loop. Whereas a do while will run the body of code at least once and then check the condition. So if this condition is always false, it'll actually execute all of this and then check the condition and then just go, oh, that's not true. So then it'll just continue on with the rest of the code. Other than that, it's exactly the same as the while loop. Next is the for loop. The for loop is a little bit more complicated in that the looping duration is actually controlled within this parentheses. So a for loop doesn't have just a condition in the parentheses. You declare a variable with some type, and then you define the starting position. This doesn't have to be 0. You can start counting at 25 or something like that. Then you do semicolon, and this second argument is the condition that gets checked at the top of the for loop. So it's similar to the while loop in that it checks a condition at the top, and this is that condition. So then this is actually incrementing up that counter. So if you remember when we were skipping through a C string earlier,
I defined some counter myself, and then I had to take care of incrementing it up. But for a for loop, that's controlled here. So if I said for int I is equal to 0, I is less than 10, I plus plus, that will loop 10 times. You can also make this incrementer more complex by doing something like this. So since the for loop is a little bit more complex, let's look at an example of for loops. So we have the same familiar C string as before, except now we're going to actually use a for loop to step through and print out the entire thing. So we're going to say int char position is equal to 0, starting at this G, while the character position is not equal to null, which is at the end of the C string, and then at the end of the loop, increment the char position up. So this moves us along the C string. For each loop that it actually does, it couts the string, and then when we actually use this in main, we end that with an end line. And that's because if we put an end line at the end of each character would be spread out vertically. So let's run this. Good morning, Starshine. The world says hello. So now let's look at what I mean if we actually added an end line here. You have to remember that we're working on character by character basis here. Compile and rerun, and there we go.
There's a couple of keywords that you want to be aware of if you're going to be using loops. You want to know about the return keyword, which you already know about from functions a little bit. This basically just completely exits out of the loop, and if it's within some sort of function, then it'll actually output whatever value that you put on the right side of the return. There's also continue, which stops the current loop and then goes back to the top of the loop structure. If you're using a loop structure like a for loop that internally takes care of a counter, then it actually counts up that counter.
Alright, that's pretty much all that we're going to cover in this video. Man, we covered a ton today. So go and get a burger and put whatever you want on it, because you deserve something for getting through this entire thing and actually grasping any of it. Yeah, it really got complicated. The great thing, though, is that we just covered probably 90% of the design tools that you're going to be using throughout most of your programming career. You'll repeatedly use a lot of these ideas whenever you want to design any algorithm. Going forward, we're going to be covering concepts that use these previous ideas that we just covered, but it's going to be organizing all of that information in different ways. This is going to be in the form of like functions or classes and objects. Alright, so thanks for tuning in. Bye! Two to make it true.